Hello everyone, in this video I'll be explaining the problem Stone Game 4. Let's read out the problem. Alice and Bob take turns playing a game with Alice starting first. Okay, initially there are n stones in a pile. On each player's turn, that player makes a move consisting of removing any non-zero square numbers from stones in the pile. Okay, so also, if a player cannot make a move, he or she, loses. Given a positive integer n, return true if only if Alice wins the game, otherwise return false. Okay. Assuming both player, plays optimally. Okay. We have just n, and we have to return true or false. If Alice wins, we have to return true. If Bob wins, then we'll have to return false. So n can go up to 10 power 5. Okay. Let's go to iPad and try to solve this. So we have stone game 4. Okay. um I highly recommend you guys to watch my stone game 1, okay, stone game 2 and stone game 3, because there in all the three videos I've been using particular pattern. uh, Alice and Bob, since there are two players and both players plays optimally, so I've been using patterns, so you'll understand. This video will understand very easily. Even if you don't follow this, don't worry, I'll be telling in detail only. But yeah, I still highly recommend, because once watch these three videos, and this video will be a simply cakewalk. So in the problem statement, what they've said is they'll give an integer n. Okay, they'll give integer n, um, which denotes number of stones in a pile. So we have just one pile, and there are n number of stones in a pile. And in the game there are two players as usual, Alice and Bob. And Alice, since she's a ladies, so ladies first. So she'll start the game. And Bob is gonna continue after that. Basically, Alice, she'll start the game, then Bob will play, then Alice, then Bob. So now, the thing is, how they are gonna play, and what's the basically game, right? So let's say we have given n number of stones in a pile. Alice, when she's taking a turn, she can choose number of stone number of stones in such a way that that number of stone is basically a perfect square. What are those perfect squares? She can choose one stone, she can choose four stones, then 9, 16, 25, 36, basically square numbers of stones she can choose. Okay. And when she chooses this many stones, let's say she's chosen 25, so your n is going to reduce by that number. Your n will be reduced by that number, and the remaining n, whatever we have in this, again now Bob is going to choose again same square number of stones. Okay. And when they're doing these operations, the player who is not able to make the operation, basically choosing the stone, he will lose or she will lose. Let's say your n is 2, so Alice is starting first. So what all stones she can choose? Okay, so uh, among this now square number of stones, she can choose just one, because if she is choosing four stones, but we don't have four stones available, we just have two. So she may choose just one stone, and she have to choose it. It's not like she'll not be choosing. It is not the way. If that is the case, then uh, let's say both the players will be in a state wherein both the players will say, I'll not choose stone, I'll not choose stone, and that will go till infinite. So that's the reason they will definitely choose stones. And in this case she'll be choosing just one stone. Okay, because four stones she can't choose, which is like we don't have that much. That's the case. So once she chooses that, your n is gonna be 1 now, because one stone is chosen by Alice. Now Bob has the capability of again choosing just one stone, because there are only one stones, and it is a perfect square, so he'll be choosing. Now your n is 0. Now it is a Alice turn. Since it's a Alice turn and she's not able to choose any stone because we don't have stone, n is 0. So in this case Alice loses. Okay, Alice loses and we have to return false. I think you guys are getting right. In this, I mean, this way we'll have to play. Let's say n is 1. So square numbers I'll be writing. So it's Alice turn first, where n is 1. So how many stones she'll be choosing? 0 she can't choose because definitely she'll have to choose 1. So among these squares, so 1 is the number of stones that she'll be choosing because others she can't choose. It is a way greater than the number of stones you have. So now n is 0 and it's a Bob's turn and Bob is not able to choose any stones. So in this case, Bob loses. The person who is not able to, make a turn, they loses. So yeah, now this is the case. Then we have to return true because Bob is, losing. Alice is winning. Since Alice is winning, so we'll have to return true. Similarly, if you consider example, let's say n is equal to 4. So what all possibility we have, right? So when n is 4, Alice is starting first. She can choose one stone or she can choose all the 4 stones. So she'll play optimally. Okay, she'll be choosing all the 4 stones. When she chooses all the 4 stones, then n is 0, and Bob he is not able to choose anything. So in this case, we have to return true. The other case is like she'll be choosing one stone. If she chooses one stone, your n is 3. Now Bob has the capability of choosing just one stone because he can't choose 4 stones. We have just 3 numbers. So Bob will be choosing one and n will be 2. So Alice will be choosing one. Okay. Then what will happen is after this thing, now n is 1 and it's the Bob's turn. So Bob will be choosing one stone and then n is 0. Now it's Alice and she cannot make. So in this case, we have to return false. But since Alice has got, she have to do an optimally, she will be definitely choosing the number of stones as 4 because when it's her turn, so she will try to optimize in a way that she is gonna, win the game. So that's the reason she'll be choosing 4 stones in such a way that there are no stones left to the Bob, so that he's not able to, make a choice of number of stones. So he's gonna, I mean, yeah, Bob is gonna lose. So in this case, we have to return true. So I think you have understood like one stone she can choose, but when she chooses one stone and it is her turn, so in the future she's gonna lose. So she'll not make that move. She will make a move wherein she is winning. Okay, it's a I think you guys have understood. Now, how to solve this problem is the question now, because both the players play optimally. Okay, so now let's understand like right algorithm. How do we, find this? What we'll try to do is um, we will call a helper function. Okay, and whatever number of stones we have, we'll be choosing passing in, and we'll have to pass through saying that it's an Alice turn. Okay, now whatever this helper function returns, we have to return that thing. Now what will be our helper function? Our helper function is gonna be en and we can say Alice turn. Okay, and it is gonna return bool either true or false. Okay, now we have to understand the base case. What would be the base case? Like when this game is gonna stop is the case. We have to understand. So when n is a perfect square, right? When n is a perfect square, the game is gonna stop because both the players, Alice and Bob, is playing optimally. Let's say if it is an Alice turn, it is a perfect square. So definitely she'll be choosing all the stones. The reason being, she will not allow in the next turn for the Bob to choose. Similarly, if it is a Bob's turn and we have perfect square, so Bob will choose all the stones, making sure that Alice in the next turn she don't have the option to choose the number of stones in such a way that Alice is losing. So both the players is gonna play optimally. So our base case will be when n is perfect square, the game is gonna stop. It doesn't matter whose turn it is because both the player are playing optimally. So we have to check if it's a Alice turn. So in that case, since in the question they've said we have to return true, else we have to return false because in case of Bob winning, we have to return false. Okay, so this thing we have to just take it. So we have got to know like what is the base case. Now, what will be our uh, you know um, the computation step, basically recursive step. Okay, so what we'll try to do is we'll have to check if it's an Alice turn. I'll be just writing the Alice turn condition and similarly holds good for the Bob as well. Okay, it's a Bob turn and it's a Alice turn. Okay, when it's an Alice turn, what you are going to do is you're basically you'll be checking the stones. What stones will be choosing? You'll be choosing from one number of stones you can choose. You can choose four number of stones. You can choose nine, basically perfect square. Okay, 16, 25, 36, up to so on. Till how much stones you're gonna choose? uh, Till this the choosing stones whatever you have is lesser than equals to n, basically remaining n. Okay, so what we'll do is we'll take I which is starting from 1 and you'll be writing I star I lesser than equals to n, and then you'll do I plus plus. I'll tell you why I star I. Okay, because let's say we are just handling with perfect squares. That's the reason. So here what we'll do is you will have to make sure um, you'll be again now calling helper function. Okay, you'll be calling helper function and your n this reduces to n minus I star I. You have got right. So because you're choosing a perfect square, so that's the reason this many stones have been reduced and your this Alice stone whatever you have it will flip its value. It will flip its value. And since it's a Bob's, block, you'll be checking if this function returns true. So you will try to lean towards that answer, right? So you will simply just return true here because we want Alice to be winning. I mean, in this block, whenever Alice is playing a game, she wants to that she wants to win basically. So whenever she gets a case wherein the answer from the base case we have written is true, which means she's telling okay that this is the one possible solution that I'll be choosing, wherein I'm winning the game. She'll be in a way she'll be choosing that way. This thing is you have understood right? N minus I star I because when I is 1, so basically 1 perfect square, 1 star 1. When I is 2, basically you'll be choosing 2 into 2, 4 stones. So from the total number of stones remaining, whatever stones you have, in that 4 stones you'll be removing so that in the next time when Bob comes, he'll be choosing the stone from the remaining stones. Okay, and this case I star I, lesser than equals to n. The reason being, let's say uh, your n is just 31 and when your I was 5, so I star I was 25, so 25 stones you can choose. But when your I is 6, so I star I is gonna be 36, so you can't choose 36 stones from 31. So that's the reason I'm just making sure I star I lesser than equals to n. So yeah, uh, and in case from like this if condition does not return true, I mean, it is not possible to win for, Alice. So after this for loop, then she will, return false saying, um, Bob is winning the game. Okay. And the same thing will go with the Bob, just that she'll be trying to optimize here when she's getting like not of helper. So in that case, she'll be rating false or else she'll be rating true. I think you guys have understood now, like how they're playing optimally. And yeah, let's go to lead code and try to solve them. And I'll tell you while explaining, I mean, while writing the code, I'll tell you everything. So first, I'll write a find square function, and then I'll write a find square root function. What I'm trying to do is basically just a pre-computation I'll be doing, because every time I star I'll not be doing, because it's an n square operation. If you would have, learned TP and you have seen like multiplication is kind of very huge operation. So every time I'll not be doing. Only one time I'll be storing these values and in a vector, and then I'll just, fetch from that vector. So in a of one time. Similarly, square root also I'll not be doing every time. I'll be just, uh, you know, write one time and then fetch the data. So um, now let's say two vectors I'll define. One vector will be square, another will be square root. So let's fill the find square function. Okay. So since n is 10 power 5, so how many squares you are gonna make? Okay, so when you take the square root of that, its value will be something like 10 to the power 2 point something. So at max, it will go till 10 power 3, because 10 power 3 into 10 power 3 if you do, it will be 10 power 6. So it is exceeding. So at max, I'll be just calculating 1000 values in the square function. I think we have understood, right? I'll take a loop from 0 till 1000 and I plus plus. And in this square, I'll be just pushing I star I, which is a square value. Now, similarly, find square root. What we'll try to do is, since n is up to 10 power 5, right? So n can be up to 10 power 5. So 10 power 5 ka square root will be something 10 power 2 plus something it will be. Okay. So so at max, what will be the size of the square root? We have to find till 10 power 5 only, right? Because it can be in the question like 10 power 5. So in that case, we have to find 10 power 5 ka square root. So at max, it will be 10 power 5. At minimum, it will be 1. So we'll be running a loop from 0 to 10 power 5. And so it will be square root of I. Okay. Here also it will be push back, not just push. I think you have understood like pre-competition what we have done. Like every time we don't need to calculate for square root and square. Okay, now we'll call a helper function. Whatever this helper function returns, so that value we're gonna return. So initially it's like Alice is playing the game. So we're passing in and we're passing bool. Let's say Alice turn. Okay. As I said, the base case will be if you have to find the number. Okay, let's call, I mean, stones, we can say. Stones will be square root of n, let me find, right? So we have, let's say, n number of stones. So we need to check if it's a perfect square or not. So we have taken square root and we have got the number of stones. Okay, so now we have to check if these stones, star stones, if it is equals to n, which means it's a perfect square, right? Um, like whatever n we have calculated its square root, and we have got a, let's say n is 36, so square root will give us 6. Let's say n is 31. The square root will be storing integer value, it will be 5. So 5 times 5 is 25, is not equal to 31. But in case of 36, 6 into 6 it will be 31. It's a perfect square. Okay, so this will take care. Now we have to check if Al is done. If it's an Al is done, we have to return true. Else we need to return false. Okay, now we'll take bool answer. Okay, we'll have to check if it's an Alice turn, then we'll play optimally in case of Alice. Uh, else Bob's turn will be played optimally. So here what you'll do is you'll take stones. Let's say I from 1, your I star I lesser than equals to n, like square numbers you're taking, right? Square number of stones. If the square number of stones chosen is lesser than equals to n, then only. If it is greater than n, then there's no point of choosing. You can't make that operation. So if you're breaking from for loop, okay. Now you'll be checking. You'll be calling helper function, and when you have chosen I is equal to 1, which means 1 ka square stone we have chosen. When I is 2, 2 ka square, like 2, 2 into 2 square stones you have chosen. So what I'll do is I'll call a square function, square vector, square of I will give me the 2 ka square, 3 ka square of number of stones. So every time you are not doing I into I here, that will be an expensive operation. Similarly, every time you are not doing square root of n here, like basically sqrt of n, when you do it's a square root function, so it will take some time. uh, it adds to the time complexity, so that's the reason. And then you will flip the Alice turn. Okay, when Alice is played, now Bob, in the next option Bob has to play. So if this function returns true, which means there is a way wherein Alice can win the game, so we need to return true. Blindly we have to return true. Else when this function is this if condition is not been executed, it means there is no way Alice can win. So in your answer, you'll store false, and at the end you're returning false. Similar thing happens with the Bob case as well. He'll be choosing square number of stones from one square. Okay, he'll be checking if not of helper will come here. I'll say y square root of I, comma, again he'll flip its she'll flip yeah, he'll flip its value. Okay, basically it's choosing square number of stones, and in case this function is returning false, which means Alice wants the answer to be false only, right? When he plays optimally, he wants Bob to win, Alice to lose. If Alice is losing, which means it is a false. We have to return false. So if Bob gets the helper function in a way wherein the value is false, then he'll be simply plainly returning false. Else, there is no way that Bob is winning. So your answer will be true, which means Alice is winning. Understood, right? This is just the recursive function. Let's try to run it. There are many test cases, so that's the reason. Yeah, now let's try to run the sample test cases. So all the sample test cases are running fine. If we try to now analyze the time complexity. So what you're doing basically, um, you're choosing I from square root. So I mean, let's say when your n is something 25. So from our function, we were choosing um, In the for loop, we were choosing stones from 1 till square root of n, okay, lesser than equals to n. So this was our case. Since like we are choosing one stone, Alice is choosing one stone, then Bob is choosing one stone, then Alice is choosing one stone. Uh, it's like one stones have been chosen by these peoples. Okay, okay. Now, when there is a case, I mean, yeah, um, still there are a lot of things like one stone is chosen by Alice, then it is Bob. Like 25 times it will be. Now, there will be a recursive function wherein now Alice is wanna choose 4 stones. Okay. When Alice is wanna store I mean 4 stones, then your n is going to be 21. And from this function calls, this where like these options will go away, and these calculations we have already done, right? So again, you are calculating like Alice is choosing 4 stones, then Bob is choosing 1 stone. Okay, so it's like there will be a repetitive states. So when there is a repetitive state, overlapping problems. So definitely, when you have already solved for that state, you need to just store in a DP. Okay, when you store in a DP, in the next iteration, you don't need to compute one more time. You just return from the that state. I mean, when you have stored somewhere value, so you need to just return. So that's the reason we need to optimize it using DP. Because there are repetitive states, and since um, we can say the time complexity is exponential. Okay, it's like 2 to power n, because whatever stones we have n. Okay, let's say one of the stones we have, these stones will be chosen by either Alice or Bob. So we have two choices, right? Since there are two choices, so definitely it will be a 2 power of n. Basically, we can say exponential. Okay, the time complexity is exponential. So since n is like 10 power 5, so this will give a lot of test case. I mean, it will be a huge time complexity. So we need to optimize it. So in order to optimize, since we are using just two states n and L is done, so we'll take a vector dp. Okay, and you're starting from n, and n can be up to max of 10 power 5. So n can go up from a 10 power 5 to 0 value. So since it is zero based indexing, so you'll have to take n plus 1 state, and this Alistan is gonna take two values, 0 or 1. So in two states we can store the value. Initially it will be -1 in order to make sure that state is not computed. Now we'll pass this TP, and we'll pass it here as well. Then before returning these answers, we need to store that DB state. It will be n comma Alistan. Okay, and here also when you're returning, just store its value. And before doing any computation, you need to check if this state is not -1, then we have already visited this state and we have stored its value, then return its value, or else it will be the 0 1. Now let's try to run it. Let's try to take the case wherein we got TLE. Yeah, this case. Now let's try to submit it. So yeah, it got accepted. So in this way, you could have easily solve the problem. So there are two things that I had optimized. I had already once calculated the square and square root and just stored in a vector, so that we don't need to calculate every time, square and square root. So we can easily fetch the data from these two, uh, you know, vectors, and it's simply a implementation. I mean recursive function wherein I've added DP on top of it. So yeah, thank you guys for watching the video.